Today we have Yoram Dagan, Professor Yoram Dagan from Colloquium University. I invited Yoram because I really enjoy the way he does science. He does the experiment first and only then applies the theory. And consequently, most of his results are very surprising. And today you show us some of those surprises. So Yoram, please.
Yes. Okay, thank you very much for the introduction, for the invitation. It's always fun to come to Israel and to see how nicely this country evolved. I'm Yoram Dagan from Tel Aviv. I'll talk about maybe some of these topics. Oxide interfaces. Basically, I'll start with the introduction to interfaces. Then I'll go to the particular interface that we are interested in. We have strontium titanate, lanthanum aluminate, and let's see how far we get from there. Okay, so whenever we have interactions between things, let's say if we have interactions between quarks, we get new species. If we have interaction between atoms, we can get something new, which is very different from hydrogen and oxygen. And if we have amino acids and we have interaction between them, we can get something new out of them, which is protein. And so I'm looking at interactions between lattices or crystals, where we grow one crystal on top of the other and try to continue the lattice structure of one crystal and grow the other crystal and see what's going on at the interface between these crystals because of various interactions that occur between these crystals. So, so examples for a few cool crystal interactions, which we have not made, but just to mention. For example, this is a single crystal of one monolayer of ferroselenium grown on strontium titanate. So here you can see this monolayer, and this is a STM image. And usually ferroselenium has a superconductivity with a critical temperature of 5K. But here, for some reasons, inherent properties of this strontium titanate. Some say polarizability, some say electron-phonon coupling, and let's not argue about that. But the fact is that TC increases by an order of magnitude when this single layer is deposited on strontium. Okay, another example is ITC cuprate superconductors. And if we look at here, you have all doping holes per copper oxygen. So ITC are made of copper oxygen planes. And you can change the hole content in these planes by adding, let's say, removing oxygen and YBCO, or adding strontium, lanthanum copper oxygen. And so here, the material is antiferromagnetic insulator, and here the material is metal and not superconducting. And here you have a superconducting dome. But if you take an underdoped cuprate and you put an overdoped cuprate, both of them are not superconducting. So this one is a metal, this one is almost an insulator, and eventually you have a superconducting with high temperature, high critical temperature at the interface between them. And so this has been shown in various works. One of them is even from here, from God. And so here they made metal, and on top of that, an insulator bilayers, and TC is, you see, is 30K, and the materials are not superconducting at all. And this is electron doped, which I like better because we made. And another example let's say if we have a material which has antiferromagnetism, so spin structure is like that, and polarization. This is just a concept, not yet realized. And polarization, which means ferroelectricity. So the material has a non-zero polarization and zero electric field. So it's ferroelectric and antiferromagnetic, and there is a coupling between the magnetism and ferroelectricity, or magnetic coupling. And so let's say if we rotate the axis of polarization by 180 degrees, also the antiferromagnetism changes sign each moment. And now, let's say this spin can be connected to a ferromagnetic layer on top via the exchange bias. So there is interaction between this antiferromagnet and ferromagnet, and therefore this ferromagnetic layer is coupled to this antiferromagnetism, and via this antiferromagnetism to this polarization.
You know, how do you get coupled between polarization and magnetization? They don't have. Conductors doesn't have time of it.
Yeah, but yeah, there are materials that, let's say, terbium manganite. There is both of them. So there is a. I mean,
you have both other quantities, but why is there a linear coupling between you reverse one, you reverse the other? I would think there would be a quadratic coupling. Polarization squared, so it doesn't matter whether.
Yeah.
Some symmetry probably. Is there a magnetic field on top of that? Or?
Yeah, there is a magnetic field. So soon we'll apply so there is a magnetic field here coming from this magnetic layer. Okay, so now there is a coupling between them, and now we want to apply the electric field, and we can reverse the polarization, and via polarization reversal we can also reverse the magnetization, and this will allow us writing ferromagnetic memories using electric field. In the electronic industry, they like to write on the electric field. So this is still a concept. As you said, it's difficult to realize, but it's possible. Okay, now you rotate the field, and then you rotate the polarization and the magnetization, and you have a memory device. Okay, and now we want to look. Oh, sorry. Too many effects. We want to look at the interfaces between transition metal oxides. So let's look at this. So interfaces are known for a while. For example, here we have an interface between silicon and silica, and this is a standard electronic device. However, in these materials, the properties of the electrons are described as it's a particle in the box. So we have free electrons. Now we want to make some more interesting physics. So we want to introduce more degrees of freedom, let's say spin, or charge, or orbital degrees of freedom, or even lattice, which means ferroelectricity. And therefore we can induce some macroscopic orders like magnetism, superconductivity, and ferroelectricity. So we want to design this interface, maybe understand them, and predict new physics. Okay, so basically our main player here is the strontium titanate. And why? It has a cube structure, and here there are oxygen octahedra. Now, at low temperatures, let's say below 103, these octahedra rotate, and there is a structural phase transition. Also, there is a very strong polarization. So this is the electric constant as a function of temperature. As you reduce the temperature, is this structural phase transition, and the electric constant increases by a lot. And this is in thousands. So the electric constant approaches 24,000 at low temperatures. And there are some claims that this is because of some quantum paraelectricity and quantum fluctuations that destroy ferroelectricity, but I'm not going to get into that. And bottom line is that this material is interesting, and it's also interesting in terms of its electronic properties. Okay, now if you dot it, and you add a few carriers into this insulating matrix, it becomes superconductor. And Tc depends on the number of charge carriers. So here it's about 10 to the 16 carriers per centimeter cube. So this is the most dilute superconductor if you want. And okay, I'll get back to that. Now if we take a look at the orbitals, so basically the conductive bands are the titanium bands, and these are Trinity orbitals, and they are split because of the lattice to x, y, y, z, and x, z, and so dxy, dyz, and dxz are split from these EG bands. So basically we're talking about these bands of the titanium. Okay, now if we confine these titanium bands, basically we are splitting them further, and now the degeneracy is removed, and dxz and dyz are now split in energy, and we get the light band here and the heavy band at somewhat higher energy. Okay, so this is the surface of strontium titanate. Now we're on two-dimensional electrons. Okay, so now let's talk about this superconducting dome. And why is it interesting, and why do we want to look at it, and why do we want to look at it inside interfaces? So first of all, this is a very interesting regime because the carriers per centimeter cube is 10 to the 16, which is very, very dilute. If you want, in a coherence length volume, you have only one Hooker approximately. And Fermi temperature is 10 K, if you just calculate it naively, while the Bi temperature is 400 K. And so this is well outside the BCS limit, where the Bi temperature should be lower than the Fermi temperature, and Tc should be lower than both. So here we have lower Tc because it's 0.4 K, but the Bi temperature is much greater than the Fermi temperature. Okay, so there have been few studies about that. For example, this is Ruchman and Patrick Lee, and they suggested some coupling to some polarization mode. And then they were yielded by Gorkov because they didn't make their own theories. But basically, there are a few other suggestions what is going on here. Okay, now we want to get to use this strontium titanate structure and maybe induce other orders. So for example, we can take a band insulator, which is like strontium titanate, and use a conducting material, which is niobium dope, as I showed you, or a mod insulator and connect it to a conducting or superconducting, and even ferroelectric and ferromagnetic, and then try to get this ferromagnetic ferroelectric coupling, which we didn't succeed in now. Okay, so how do we make the samples? So this is just a sample preparation for your amusement. And so we have a pulse laser deposition, and we know from here, also that Coren did that a long time ago. And basically we want to grow layer by layer. So we start off with strontium titanate, and basically we can smooth it using some chemical process. And eventually we get a step structure, and this is 4 angstrom step height. And this is about, it can be even half micron or 1 micron step, which means that we have a football field and then a very small step after that. So it's a very flat surface. And it's a TiO2 terminated because TiO2 is very stable for chemical reactions. And basically this is what survives this hydrofluoric acid. After that, we can deposit using a PLD. And we also have electron diffraction in situ. So we can look at the diffraction pattern while the layers are deposited. And basically, the diffraction is at maximum when you have a complete layer, or the intensity is maximum when you have a complete layer, and then when you grow more layers, you get a disordered surface in terms terms of 1 unit cell, but you have a minimum and a maximum, and this is how you can count the number of unit cells that you are depositing. Okay, so after we know how to do that, we can basically look back at this paper, which is kind of seminal. So this is Otomo and 1. And this paper opened all this fuss about these interfaces. And so they took strontium titanate, made this process, and deposited lanthanum aluminate, a few layers of lanthanum aluminate, and they found out that if the strontium titanate is SRO terminated, the material is insulator, while if this strontium titanate is TiO2 terminated, you get a conductor. And when you deposit lanthanum aluminate. Okay, just a reminder that both parent materials are insulated. So these are two insulators, and you get a conducting two-dimensional electron gas between them. Okay. Another very interesting feature is conductivity threshold. If you deposit 1 or 2 or 3 unit cells of lanthanum aluminate, the material is still insulated. While if you grow 4 unit cells or more, you get conductivity very suddenly. So this is an abrupt change from an insulator to metal or to a 2D gas. And also this is in carrier concentration. So you have a conductivity threshold of 4 unit cells. And this is important for the next part. Okay, what's the origin of the carriers in this interface? So if we carefully look at the strontium titanate, it's non-polar material, but lanthanum aluminate has a polar structure. For example, lanthanum oxide is plus, has a plus charge, and aluminum oxide has minus charge, and it goes like that, as many as LAO lanthanum aluminate layers that we deposit. So this is the charge distribution. So here we have a plus charge, minus charge, plus charge, minus charge. And now we can calculate the electric field. We learned that in physics 102, whatever. So here we have a positive electric field, and then we are outside the capacitors, we have 0 electric field, and then again we have electric field, and now we integrate over the electric field, and we get the capacitance. Here, so you can see it. So we get the electrical potential. So the electrical potential increases and then stays the same, and then increases further and further beyond. And of course, it cannot increase forever, and eventually we'll have the band gap of strontium titanate, and we get a charge transfer to the interface. Okay, so because of this Coulomb potential, we have a transfer of charge to the interface, and if we calculate how much charge do we need half electron per unit cell approximately, because if you do that, then here you have half electron, plus minus, and now the electric field is alternating, electric potential is not diverging, and we are all happy, and the material is not, does not have diverging energy, but for that we need 10 to the 14 carriers. Okay, so why, if LAO is so polar, why isn't it, is it polar also if you take a piece of lanthanum aluminate? Okay, the answer is not, of course, no, because you can reconstruct. If you take a piece of lanthanum aluminate, immediately reconstruct, you cannot make a smooth surface of lanthanum aluminate, but here you force it to grow in the strontium titanate, and this way you can hold this polarization. Okay, now there has been more complicated calculations of what's going on here. So this is a DFT calculation of the band structure of the interface. So you see 1 unit cell, there is a gap here and no states. And then as you add more and more lanthanum aluminate layer, you have states here, and then you have conductivity. And so they predicted conductivity at 5 unit cells. Of course, they predicted it after the experiment. As Amit said, we always understand the theory after it's been proven in experiment. Okay, so other explanations do exist. For example, electronic mixing or oxygen vacancies. So these are just 2 pieces of strontium titanate that we took in the lab. This one we baked in the furnace. This one we did not bake. And this one is black because it lost oxygen and it is conducting. Okay, another thing that can happen is mixing between lanthanum and strontium, and this also can also make a tiny contact between these interfaces. At the interface, but let's say this TDM study, so here you see the atoms and here you see the elements, shows that these effects are not so important. Okay, they do exist, but they are not the main reason for conductivity. Okay, now this 2D has 2D electron gases on top of strontium titanate. The electric constant is 24,000, and you can apply gate voltage. So basically you can apply rather small electric field and you will get a strong response. So this is what they did here. This is the group in Germany, Mannhardt. And here you add, you put 3 unit cells, so it's almost at the threshold for conductivity, but it is still insulated. And then you apply gate voltage, and then you turn on conductivity. So here, gate voltage is 0, then you apply gate voltage, and you have conducting, and you can turn it on and off. Okay, this is nice. And also another nice application is using conducting AFM. Instead of biasing using gate voltage, you can use AFM-T. So this is a conducting AFM-T. Basically, you bias this T against the surface, and you grow the material here, 3 unit cells. So it's almost an insulator or almost a conductor, and then you apply this electric field, and then you can induce conductivity locally. And this way you can write all sorts of devices just by using AFM-T. For example, they just wrote quantum dot. And just before we published our quantum dot. Okay, too bad, but it's a nice technique, I must say. So here they wrote a sketch, they call it sketch FET, so this is a field effect transistor, so this is the gate, and this is source and drain, and they can apply the gate from here, and therefore induce conductivity in this small part here, which is not connected. And these are the characteristics of this device. Okay, so very nice. And now there are also real devices circuits. For example, this is done also in Germany. So this is lanthanum aluminate, strontium titanate, and these 2D electron gas here, and titanium contacts. And this is top-gated by YVCO. And these are the characteristics. Oops, sorry. Okay, maybe a very important fact about these. So these are many transistors on top of a big device, but they're all N-type. So if you're engineers, so you know that modern electronics cannot be used with these transistors. Okay, there are no P-type oxides yet. We are working on that though. Okay, now going back to our favorite phenomena, which is superconductivity. So if you apply gate here at the interface, strontium titanate is superconducting, and maybe this interface is also superconducting. It has strontium titanate, it has strontium titanate bands, so it can be superconducting, and it is. So this was found in 2007. So you have superconductivity, and this is a superconducting dome, which resembles the cuprate. But TC is 300 millikelvin, and not 100 Kelvin. Okay, so TC is lower, but it can be controlled very efficiently in a continuous fashion. Let's say if you want to look at ITC, usually you have to grow many samples in various dopings, but here you can study the phase diagram in a continuous way. Okay, so now we don't want to look at superconductivity. So we also did that, and this is the gate-controlled superconductivity, and we applied parallel magnetic field, which was done some time ago, and we looked at the upper critical field, and we found it to be just parallel to the two-dimensional electron gas, and we found it to be very large, because now you apply the magnetic field, and you have basically you have a Cooper pair, and you can know the energy of the pairing just by calculating it from TC. And basically there is a limit, which is called the Goldstone-Chandrasekhar limit, which means that at some point you will align the spins and then break superconductivity. So this is upper limit for any superconductor, but here this limit is exceeded by the upper critical field for parallel field, which means that we have a strong spin-orbit interaction. If we have strong spin-orbit interaction, and this condition is relaxed, or if it's not S-wave. Okay, but it's a 300 kK, so probably it's S-wave superconductor, and now we have a strong spin-orbit, and spin-orbit interaction changes with electric field, which is also very nice. So we have a tunable spin orbit, which is about 3 milli-electron volts of the order of the Fermi energy, which makes it also an interesting system for spintronics applications. Okay, maybe I will not talk about magnetism, but there is magnetism there also. And let's focus on superconductivity. And then I'll show you this one. Okay, so we want to understand how come, now this is Thomson catenate, okay? And if you project the superconductivity found in this to the electron gas on this phase diagram, you find it to be very narrow, okay? So perhaps here you have some kind of fluctuations because it's a two-dimensional system, so the fluctuations should be very strong. But what is going on here? We don't know. So I want to understand this phase diagram of superconductivity. Okay, another important fact is that we have two bands. So this is the Shubnikov-Haas measurements and Hall measurements. Basically, these are measurements of you put strong magnetic field, and you look at the resistivity, and resistivity oscillates, and the frequency 1/h is proportional to the area of the Fermi surface. So this is a direct measurement of the carrier concentration, but for that you need high mobility, which means you need electrons that can make a circle around the Fermi surface, a full circle, or a full path. So basically this is a probe of the mobile electrons that we have in the sample. And if we calculate how many electrons we have, it's a direct calculation that we learn third year in physics. And so you find 10 to the 12 electrons per centimeter squared. And now you can also measure Hall effect, that this is all up to 32, and you see that Hall is not linear, okay? So we have two bands. And we can calculate the Hall and carrier concentration from both measurements, carrier concentrations from both measurements, and we see that they do not reconcile. For example, here this is the Shubnikov-Haas multiplied by 6, and these are the two bands from the Hall. Okay, if you just naively assume two-band conductivity. Okay, so this is a problem. Okay, we know that there are two bands because there is a large null signal and thermal power behaves very in a peculiar way, and we will not get into that. Okay, and we know that what's going on. So these are the titanium band that I showed you, and they are split, and now we have this DXY band, and then DYZ, DZ are right here. So we expect to have, let's say, if we are populating up to here, this potential well, we have both types of carriers. And so, okay, these are the questions that I try to answer. Why superconductivity decreases on the overload side? which band is responsible for superconductivity, and why Shubikov the Haas and Hall do not fit. Okay, so we looked carefully at Shubikov the Haas, Hall, and superconductivity with gate voltage. Okay, it's a lot of work, and we had to go to Tallahassee, magnet lab, and to Nijmegen, in Holland, other magnet lab. In Nijmegen, the magnet didn't work. We need to go again to Tallahassee, and eventually we get the data. Okay, so this is the superconducting dome in our device. It's a small bridge, so it's very efficient. And here we have high resistance and voltage. So quite narrow gate voltage range. And here you have superconductivity, this is zero resistance. And basically this is DC, this yellow line. Okay, and now we can measure the upper critical field, and we can look at the superconducting properties. Now this is gate voltage, and this is upper critical field, or DC, it's also called that. And this is the low field Hall. So this was the first surprise, because this low field Hall follows this dome of the superconductivity. Okay, so maximum DC is where maximum Hall is. But Hall can tell you nothing because, as you saw before, carrier concentration extracted from Hall is very different from Shubikov the Haas. Okay, so we looked at this Shubikov the Haas at high field. It's not that high actually here, it's up to 18 Tesla, but it's low temperature, it's going to be Kelvin. And now we can follow what's going on in Shubikov the Haas. So Shubikov the Haas frequency basically is carrier concentration increases as you add carriers, then you try to add carriers, but then the frequency decreases, which means you apply positive gate voltage on your capacitor, you try to accumulate carriers, but the number of carriers is decreasing. And also the same thing happens with the inverse Hall coefficient. So is it a breaking of thermodynamics? Law of thermodynamics, so we have a negative capacitance here, and the answer is no. Okay, Q is CV, and C is positive. So total charge is of course increasing, but for some reason the charges that we saw decreased. Okay, so we thought about it for a long time, and then Moshe Goldstein came to our department, and he suggested that maybe there are interactions between the bands, and therefore they repel each other. So he knows that from quantum dots. So let's say you have two bands, and then you try to populate these, and you have interaction. Electron-electron interaction, or some kind of Hubbard model. And then you increase the chemical potential. Now this pushes this band away, and eventually you populate this band, but when you try to populate it more, actually it's favorable because of the high density of state here to pour carriers back into this band. So basically, the number of charge carriers in this band is non-monotonic, or if you want, the band structure is not rigid. So it is changing when you change the chemical potential. Okay, and we started, so now we have to build a model because Moshe Goldstein is also there. And so we use this starting point of Joshua and Ruchman, basically Ruchman and Ehud Altman, and they looked at this spin-orbit split titanium bands, and they found that these bands split, and now we had to add a more complicated stuff, which is this interaction. Okay, so this is their model, let's not. Okay, just know that we calculated it, so we put some average U, and here it's the average carrier density, and eventually we can calculate what's going on, and calculate the new band structure. So this is the new band structure, and now you see it's not rigid, so we increase the chemical potential, and the band structure is changing. So if you look at this band, initially you have very low carriers here, then you have many carriers, and then you have less carriers. Okay.
Excuse me.
Yes.
On the horizontal axis, you put a K. What does K mean?
Here, this is energy. Okay, and
Yeah,
this
but
is
K.
the function of K.
What is K?
K is the
Do you
momentum.
still have translational symmetry?
Yeah, sure. Of course. Yeah, it's in the lattice. Now you have, this is Brillouin zone or whatever. And now you have, you look at the energy as a function of
The
momentum.
translation seems to be this way, but not.
No, this way of course not. Sorry. Yeah, it's a two-dimensional system.
But why do you have the same constant in the different layers?
Okay, because it's, you mean for all the bands. So why is U is the same for all of them? Because otherwise it would be difficult to calculate. I mean, this was just a starting point.
There is the same unit cell for all the layers?
You mean for all the bands? Yeah, the same unit. We use the
No,
same.
he's asking about unit cell size from the interface down. Is the unit cell size the same?
Yes,
As it goes
it's a
down?
cubic. It's a cubic structure, but basically now you have only a two-dimensional system. So this is an insulator here, it's an insulator here, and you just look at the interface between them. This is the system that we look at. Did I answer the question?
Don't the layers have different unit cells?
They have almost the same unit cell. And also because of this epitaxial growth, this lanthanum aluminate is deposited on top of strontium titanate. Basically, it takes the unit cell from the strontium titanate. So it is slightly strained, but very slightly. The unit cell is quite similar. But you're right, yeah, if we go very thick layer, eventually the strain will relax and we'll have some kind of dislocations. Now, no dislocations. This is why we make it thin. Okay, so now let's look at the carrier density. Okay, I think we'll finish soon. And so carrier density, now calculated from this band structure, is non-monotonic, and this is the density of states, also non-monotonic. Okay, so this is very nice, because now we can assume that this band 2, I mean, this is just a rough assumption, but if we put this density of states in BCS model, for example. Okay, let's do that. So basically, in the BCS model, you have a density of states here and omega divide, or something, or omega something. So we can predict TC as a function of gate voltage. And okay, so divide temperature we just take from strontium titanate. I know that this is not totally legal, but we can do that. But basically, it doesn't matter. It is just an energy scale, and then we can change the coupling here. And it's a weak coupling limit. Although electron-phonon coupling is very strong, but still, delta over KTC is 2 delta over KTC is 3.5 for reasons that we don't understand. And then we can just generate this dome, just from these transport measurements. Okay, so we're not claiming that this is the explanation for the superconducting dome, but it's a plausible explanation, and we can predict the dome just by a simple argument. Okay, so cubic of gas, Hall and TC exhibit the same behavior. And electronic correlation explain peculiar transport properties, and all transport properties are reconciled now, and we assume 2 bands superconducting BCS, but only with 1 band participating, not 2 band, and 2 band and correlation can make a dome. Okay, and now in the last 10 minutes, I'll go from 2D to 1D. And then I'll let you ask questions. Okay, so let's look at this conventional interface. So again, we deposit one material on top of the other, and we are interested in at this place. So basically, if you want to make a so this is some other interface, Now, if you have this 2D interface, you want to make it 1D, and you can do it by brute force. Basically, you can etch it away in the lab, and then have a very narrow constriction. And let's say the length scale here is a Fermi wavelength. So basically, if you want to be 1D strictly, you have to make this narrower than Fermi wavelength. In our case, it's about 1,000 angstroms. Okay, and 100 nanometers, depending, of course, on carrier density. The problem with all these processes that they induce contaminations and also spurious conductivity, because in our case it is strontium titanate, and strontium titanate, you just remove some oxygen and it becomes conducting, and it's a problem. Okay, so then we came up with another idea. Basically, it's a suggestion of Technion alone. Now a postdoc in Caltech, David Shibu. So he said, okay, we have a discontinuity in this direction. Let's go back to this slide. Okay, so we have discontinuity in this direction. Basically, we have oxide A, and then polarization changes suddenly at the interface, and we have a two-dimensional electron gas. Or as I can see it, you see we have polarization here, which is strong, here, which is weak, and then you have a two-dimensional electron gas, because you have discontinuity in the z direction. Now, what happens if we make a discontinuity in, let's say, the x direction? So we take interface A and interface B. So both of them are not conducting. So interface A, let's say it's 1 unit cell of lanthanum aluminate on top of strontium titanate, and here no conductivity, because you are below the conductivity threshold. Interface B, it's also non-conducting, but let's say it has 3 unit cells of lanthanum aluminate on top of strontium titanate, below conductivity threshold. And here you have an abrupt change from 1 unit cell to 3 unit cells. Okay, so this is a discontinuity along this direction, and of course discontinuity along this direction. Okay, so we have 2 discontinuities. So he hoped that we'll get a one-dimensional conductor. That time he was just starting, so I told him, okay, go and try that. Why not? And I said to myself, it's not going to work, of course. Okay, so he tried that. And okay. He explained to me why he thought about that. Let's say in semiconductors, if you take this band structure seriously, so you have discontinuity when you have a small gate and large gate. But forget about that. So he made this device, and now, surprisingly, it was conducting. And if you look at the temperature dependence, resistivity increases, okay, and then decreases, and then shoots up at low temperatures. Okay, so this is temperature, this is just the resistance of this 1D structure. And just to mention that all these layers are not conducting at all. So only at this one-dimensional separation there is conductivity. And okay, so we interpreted that as a period freezer. And here we have this scattering, phonons.
That's resistance.
Yeah, this is
Go back to the graph.
This is just a sketch. But this is insulating.
No, that I understood. Not the graph. Because you draw a graph of resistance.
Right.
So
So
it goes up.
yeah, so resistance goes up. Did I say conductance goes up?
Yeah.
Ah, okay, sorry. Mistake. Okay. So here resistance goes up, and here resistance goes up. Sorry. Okay. So confinement is formed. Is it a quantum confinement? So yes. So we look now. We have to change the gate voltage and look at the conductivity as a function of gate voltage. And we know for Landauer that each channel should contribute E squared over H. And if they are spin degenerate, then each channel should contribute to each E squared over H. Now when he made the first device, it was many devices in parallel, but conductivity adds up, in parallel. So basically, every step here means opening up of a channel in one of the wires, or maybe only one wire is opening many channels. So 2 channels, 3, 4, 5. Another interesting thing is that this is E squared over H, not 2 E squared over H, which means that spin degeneracy is removed. As Amit warned you, don't ask me why. Okay, but we know, at least we know Landauer formula, so G naught is 2 E squared over H, and let's say if Ti is 1, you add just G naught, and N is just the number of channels, and spin degeneracy is removed. Since then, we made many other devices, so let's say here, you have, temperature is not so low, because we have no dilution fridge, but we bought one. So soon we have one, but this is only one step. It's E squared over H. And now if you look at the temperature dependence, you see at 4K, this step is gone. And you see only one step. And this is also a single device. So you see here 5, 6, I don't know what these are, 8, some resonance. Okay, so also important interesting stuff is that this is actually an interface between 1 unit cell and 2 unit cell. So this is 1 and 3. So this is also forming a quantum wire, which is also nice. So also 1 and 3 and 1 and 2. And this is not published yet, but we're waiting for our big fridge to make many more of that and be able to study that as a function of field and temperature. Basically, the magnetic field perpendicular to the sample does nothing to that. So I will show you this plot, and this is various magnetic fields up to 6 Tesla. Okay, okay, so this is just a summary. I showed you this superconducting dome with correlations, one-dimensional wire with the spin polarization, and basically these are the guys who did all the work. Yoram Dagan, the son of Big Maniv, and Alon Ron made the wires, and Moshe Ben Shalom in the transport properties. He's in Manchester now, and Alon Ron is now in Taipei, and Yoram Dagan is still in Tel Aviv. Okay, and thanks of course to the Magnet Lab people and Arik Walewski and Moshe Goldstein. Thank you. Questions?
When you get to the low level, so it's just two layers. Only find factors,
Right.
and where they join them. How do you do that? I don't understand it. Well,
yeah, this is why I thought it's not going to work. And I told Alon, go and try that, just as a practice. I don't know why it's working.
no, but the question is
it a straight line? Is it a straight line? It is straight line up to the photolithography. But it's nothing, yeah. It's a gigantic scale, it's very coarse. Okay, and also we try to define it with e-beam lithography, actually we do the worst job. So it is defined by photolithography. Also the wires are very long, so this is also surprising. They are 1 micron long. If you compare it to the mean-free path in this material, mean-free path is like 1,000 angstroms if you're generous. And also if you look at the phase coherence length in the 2-dimensional system, it's about 1,000 angstroms too. So this is larger than both length scales, which is also surprising. But for some reason, it's working. So there is some kind of protection against backscattering. We interpret that as a result of magnetism and spin-orbit interaction, but this is still to be studied and understood.
So this looks like a single spin ferromagnetic channel, right? That's
right.
So if you put a magnetic field coupled with a Zeeman, Do you see the steps changing, the voltage steps randomly?
Yeah, that's a good question. Unfortunately, our magnet in the low temperature system is only horizontal. And if you want to put the sample again, if you take the sample out, put it back in, sample is dead. And because it's a wire, and wire is very sensitive. But soon we'll have a 911 vector magnet, so I'll have a good answer to you. But we only apply field perpendicular. Well, let's say we try to apply
perpendicular strong field should couple to the spin, change maybe the distance between the steps.
Yeah, but 6 Tesla is not a lot. So let's say, yeah, so maybe in this 1, 2, maybe 6 Tesla can do something because it's 4 Kelvin can destroy the steps. But 4 Tesla would not do much with the standard wire. But this is something to be studied.
God.
You have a weird superconducting dome. No, not here, the 2D.
Yeah.
The red and blue. Why is it going up, this one? Why is it going down so sharply on the two sides? It's unlike the Cooper, it's unlike anything that I've seen before.
Yeah, so here it's definitely going down sharply, so the transition is quite sharp. And here, maybe it's too sharp. I don't know. So let's say on this part, I cannot guarantee that this is the size, because also the resistance here is very high. And maybe we can do some of the contacts, but this is definitely sharp. I agree that this is not well explained.
So I have one question. Can you take anything from your study with the gate voltage, creating a dome with the gate voltage to the cuprates? Is there any insight you can gain between one
People
approach?
try that, but not with the bottom gate, because there you need gigantic field, because carrier concentration is 100 times larger, maybe.
When you change your gate voltage, you change
You
carrier
change carrier
concentration by a
concentration.
factor of 100.
No, you need to change. You need, in the cuprates, you need to change to something like
From 5% to 25%.
Yeah, so that's a lot.
Okay.
That's a lot. Here it's very dilute. The system is 10 to the 16 per centimeter cube, or 10 to the 12, 10 to the 13 per centimeter square. So it's a very dilute system. This is why it is so. And also the electric constant is gigantic. With the cuprate, if you apply gate voltage from Strontium titanate, maybe you change by half a Kelvin, if you're really lucky. And you have really, really thin something. Unless you are Hendrik Schon.
Okay, so if there are no more questions, let's thank Yoram.